Hello all, myself Sambasiva Rao, working as Assistant Professor in the Department of Civil Engineering at VIGNANA VJEC. I welcome you all to the lecture series on payment materials, and the topic of discussion for today will be Marshall method of mixed design. So this will be a part 2 for Marshall method of mixed design. We have covered the part 1 session of the Marshall method of mixed design in the previous lecture. So kindly go through that lecture before coming to this lecture. So I'll just recall the topics which have been covered in the part 1. So these are the different layers in the flexible payment, where we are going to have bituminous layers like surface course and the binder course in the form of BC and DBM, followed by granular layers in the form of subbase and base course, and at the bottom we are going to have subgrade, and below which you are going to have an embankment. And there are also some layers which are present in the top side, which is nothing but like seal coat, tack coat, and prime coat. The seal coat is to seal the surface of the wearing course, followed by tack coat is nothing but a connection between two bituminous layers, and prime coat is nothing but the connection between a unbound layer and the bound layer. So next one, this is the image which I have taken previously from ISC 37, and you have looked at the critical locations for fatigue and rutting conditions. For rutting, it will be the vertical compressive strain at the top of the subgrade at this condition, and for horizontal tensile strain at the bottom of the bituminous layer will give an indication about the fatigue that has happened in the bituminous layers or the entire pavement layer. These are the different steps which we have looked into the Marshall method of mixed design. First one, you have to select some particular grade of aggregate and source of aggregate along with the different gradation of aggregate, and then you have to select any bitumen according to your convenience and according to the site conditions, and you have to prepare the trial mixes with the selected aggregate and selected bitumen, and you have to go for trial asphalt contents, and you have to prepare samples. So preparation of trial Marshall samples will happen at 4, 5, 4.5 and 5, 5.5, 6 like that. And compaction, you have to go for compaction. Before that, you have to heat that bitumen and aggregate to the required temperatures, and then you have to mix both of them either using manual mixing or automatic mixing, followed by compaction, again manual compaction or machine compaction, followed by then you have to suppose to conduct the stability and the flow test. So this is nothing but a Marshall test. This is the actual test what is very important over here. And then you have to also required to calculate the density and air voids calculation. Already we have seen in the previous lecture how to calculate GMB bulk density and GMM theoretical specific gravity, followed by we also looked at how to calculate the VMA, voids in mineral aggregate, which is nothing but VA plus VB, and we also looked at what is VFB, voids fluid with the bitumen, which is nothing but VB divided by VMA, and then you have to find out the optimum binder content selection. So you have started your trial asphalt contents at 4, 4.5, 5.5 like that and all. So you have to see what is your actual optimum binder content for a given aggregate gradation and for given bitumen type, and then you have to proceed your further testing at optimum binder content. First, everything is a trial process. Once you arrive at OBC, at that OBC, you are going to check the the Marshall stability and any other performance testing, and then final mix verification. So this is what we have looked at. This is a loose mixture prepared at the plant, and this is a loose mix that is transported to the site and it is compacted, and then this is the loose mix that is being prepared at the laboratory, and these are the samples that has been casted at the laboratory. So this is the automatic mixer, and this is automatic compactor, and this is a Marshall mold, here Marshall mold, and this is a collar mold, and this is a base plate over here. And then this is the grading requirements of the bituminous concrete, which is nothing but a wearing course of BC1 type and BC2 type. This is a thickness of 50 to 65 mm. Previous lecture I have mentioned this as sieve size. Just make a correction. This is nothing but thickness of the layer 50 to 65 mm, and this is a thickness of 30 to 45 mm, and these are the different gradation that we are going to have. 100% of finer, which is nothing but cumulative percentage passing. 100% of metal is passing. Only 70 to 95, 90 to 79 to 100% of metal is passing through that. It means nothing but some percentage weight of the metal is retained over here. And then this is how we worked out how much amount of metal is being retained on each and every sieve. And after that, this is upper limit and this is a lower limit, and this is midpoint gradation is blue one, and our mix formula what we have taken is nothing but green one. And then this is how we prepared a mix, and we have looked at the three-phase diagram system, and we looked at the calculation of volumetric properties like air voids, VMA, VFB, and then we also solved some couple of problems on this Marshall properties. And then today we are going to look into this Marshall stability and Marshall flow. Previously I have got the Marshall samples which are of 100 mm dia and 63.5 mm thickness. So these samples you have to conduct GMB, which is nothing but bulk density. Either you can do it taking the weight of the sample divided by volume of the sample. This is one way you can do it, or else you can take weight in air divided by weight in saturated surface dry weight minus weight in water. That is also you can take. So either of this you are going to get the bulk density, which is nothing but GMB. You are going to get GMB like this. Two methods are there. One is nothing but weight by volume relation, other one is nothing but you are going to get it from weight in water to weight in air and saturated surface dry weight. And then it is nothing but very important. And some samples you have calculated Marshall properties like volumetric properties, and then you also required to conduct Marshall stability and Marshall flow. So this is the machine which I am having over here. So this is the Marshall test setup. So here this is the jig what we are having. So this is the semicircular jig on the top side and the semicircular jig on the bottom side, and you have to insert your specimen in the middle. The test temperature is nothing but 60 degrees centigrade. You have to keep the sample for 2 hours at 60 degrees centigrade. That is nothing but the conditioning, which is going to represent the higher temperature conditions. Bitumen becomes softer at 60 degrees centigrade. So that is why we are targeting your high temperature criteria. So this is a representation for high temperature conditions, and the rate of loading is nothing but 50 mm per minute. So this is you are having a DAQ where data acquisition cell will be there, where in which you are going to get the load cell. One is nothing but one cell will be denoting load and another one will be deformation cell. There will be two cells, and this is the load constant deformation loading rate you are adopting, and this is the diameter of the sample and thickness of the sample what we are having. Now I'm keep on applying the load over here, and the sample is going to take on some load. While the sample is taking some amount of load, there is also some amount of deformation that is going to happen in the sample. So that will be captured in the form of a like this. So there is a graph over here. So once you start applying some load, okay, once the bitumen is taking some load over here, so it has taken this much of load, but at the same time it has underwent this much of deformation. After some point of time, after applying this much of load, okay, it has went deformation of this much, from zero deformation. So it went off deformation like this, and this is the peak load, and you have to take the deformation corresponding to this value. So this is a peak load of somewhere around 24,000 newtons. So that is nothing but 24 kilonewtons. And the deformation corresponding to this is nothing but 12 mm. So this is the DAQ what you are going to get. Now I'll see the definitions of the Marshall stability. Marshall stability is the maximum load. Simply it is nothing but the load that a compacted bituminous sample can sustain at 60 degrees centigrade when loaded diametrically at a constant rate of 50 mm per minute. So that is what the simple definition of Marshall stability. It is nothing but the maximum load that a compacted bituminous sample at 60 degrees centigrade that is going to take, the load that is going to take. And next one, the significance of this test is very important. It indicates the load carrying capacity of the asphalt mix. You are going to get the load carrying capacity of the asphalt mix. Higher is the load that is going to taken up by the Marshall specimen, higher is the stability, or higher is the resistance to rutting, or higher is the resistance, higher is the it is able to work for high temperature conditions. So that is what it has been represented over here. Higher stability, better resistance to rutting and shear deformation and traffic. Excessively high stability may indicate a brittle mix. So you are going to have excessively high stability, which means nothing but the material is just like, instead of being like a elastic material, it becomes like a brittle material, just like a concrete. It just shatters like that. It just undergoes like brittle. That is also not encouraged. So we need to have a medium amount of stability. At the same time, what is Marshall flow is nothing but Marshall flow is the total deformation that the specimen undergoes at the point of maximum load. I've just represented over here. This is at the point of maximum load. What is the amount of deformation that is happening? So this is the deformation that is happening, and this is the load. At the peak load, what is the deformation that I'm having? So that is what the Marshall flow. And it represents the flexibility and the plasticity of the mix. Here low flow represents mix is stiff. When the mix is stiff, when you are applying the load is also, then there is no amount of deformation that is going to happen in the sample. So that is nothing but the mix is stiff, then only, and it is brittle, then you are going to have low flame. But when the mix is stiff, then you are going to have excessively high stability. And high flow is nothing but mix is too plastic. So we are not going to encourage either high flow is also. It means nothing but mix is very soft. Okay, that is not considered. So this is how this is one sample, one screenshot that is taken while the testing of Marshall stability at a laboratory. And these are the test conditions, and this is the Marshall test setup, and this is the jig what you are having. This is the load cell, and this one is load cell, one is a deformation cell. And this is after doing everything, I have got the volumetric properties like this. So I've got the bitumen trial content, I have taken 4.5, and I have taken 5% bitumen content, 5.5, 6%, because I don't know what is the optimum binder content. And after that, I have taken the weight in air, weight in air, weight in air of all, each of the sample, and weight in water. From that, I've got what is meant by GMB. GMB is nothing but weight in air divided by weight of the saturated surface dry weight minus weight in water. So from that you are going to get what is GMB, bulk density, gram per cc. And you know how to calculate GMM. It is nothing but total percentage weight of the total percentage of the metals divided by percentage weight of the metal 1 divided by specific gravity of the metal 1 plus something like that. Okay, and then you are going to get what is percentage of air voids, VA, which is nothing but GMM minus GMB divided by GMM. And then you know how to calculate VB, we also looked at, and then VMA followed by VFB, and this is the stability and the flow. So these are the different values which I have got it. Now I'm going to plot some graphs. So these are the different graphs. So I've taken at 4%, so 4.5%, this is the value, 5%, 5.5, 6, 6.5, like that. So once you got this, I've told you that OBC is corresponding to three figures. One is nothing but air voids, the corresponding air voids to 4%, corresponding at 4% air voids, what is the bitumen content. So that is one thing. So this is one, B1, bitumen content 1. And this is again Marshall stability. It will be keep on increasing till one point of time, till some point of bitumen content. And after that, if you increase the bitumen content, there will be a reverse trend of the Marshall stability. And this is the corresponding bitumen content. This is also very close to 5.5. And again, the other one is nothing but unit weight, bulk specific gravity. This is also very close to more than 5.5, something like this. So you have to take this as B3, and this is B2, and this is B1. These are the approximations. So once you, this is how, again the same thing which has been represented over here. This is Marshall stability value, and this is the unit weight value. I've told you Marshall stability is going to increase and decrease, and unit weight is also having more or less the same trend, and volume of voids will be keep on decreasing. As the bitumen content is increasing, the voids will be keep on decreasing. Why? Because we have a mix like this, and we have VMA, that is nothing but voids in mineral aggregate. So this space has to be occupied by both VA and VB, that is nothing but air voids and bitumen. As you keep on increasing the bitumen, so the space is the same space, but you are keep on increasing the bitumen content, so therefore air voids will be keep on reducing. So these are the three graphs, 1, 2, and this is the 3, corresponding to 4% air voids, what is the bitumen content. So you have to take the average value of all these three. So that is what I have represented. The optimum bitumen content is computed as the average of the bitumen content selected corresponding to maximum stability value 1, maximum bulk density 2, and 4% air voids. So in this condition, this is another calculation where in the previous I have taken it as 5.5, like that. So approximations like that you have to do for your testing conditions. 5 plus 5 plus 5.5 divided by 3. So I've got it to be 5.33 is the OBC, optimum binder content. So for the set of aggregate, for the gradation of aggregate what you have selected and the type of the bitumen you have selected, your optimum binder content is nothing but 5.33. Now you have to again cast your new specimens with this optimum binder content of 5.33, and then you are supposed to do this original testing again, and then your optimum binder content is 5.33%. So for bitumen gradation, you will be having the code book, or you'll be having MS2 manual. So you have to check what is the limiting values of bitumen content. Yes, it is should be between 5 and 7. I have got the value between them. And bulk density, there is no code requirement, so I've got 2.369, which is valid. And voids in compacted mix, it should be 4. I've got it to be 4, and it should be 3 to 5. So I've got it to 4 at OBC. This everything is going to happen at OBC. And again, after casting the specimens at optimum binder content, I'm going to check the what is meant by stability. So I've checked the stability to be 1670 kg, and here it should be minimum is 900. So that is also fulfilled. This should be minimum, and I have got it to be 1670. And Marshall flow, there should be value between 2 to 4, and this is also I've got it to be 4. And percentage air voids filled, it should be in the range of 65 to 75, and this is also fulfilled. So now you are almost your criteria for job mix pharma is okay, because you have fulfilled everything at optimum binder content. Now whatever the bitumen content what you have taken, whatever the aggregate you have taken, whatever the bitumen content you have taken, what is the source of bitumen you have taken, what is the grade of bitumen you have taken, everything will satisfy, and that itself you can establish that as a job mix pharma. If any of them is not being fulfilled, then you have to change the gradation of the aggregate or the source of the aggregate, or else you have to change the grade of the bitumen, or else you have to change the source of the bitumen. Okay, like that you have to keep again take different gradation of the aggregate, different bitumen, and again take trial asphalt contents, and again start doing calculating of Marshall properties, and along with volumetric properties, go for plotting of the graphs, and again get OBC from 1 to 3 graphs, and take the average value, again go for casting of the specimens at OBC, and again go for testing of the these conditions at OBC. If that is fulfilled, then at condition at which where you are satisfying each and everything, then you end up in designing the mix. So that is nothing but mixed design, Marshall method of mixed design. So this is the conclusion of the Marshall method of mixed design. I sincerely acknowledge the use of publicly available resources that supported and enhanced the visual clarity of this presentation. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.